Let me just turn on my clock here.
Is it an atomic clock?
How do you turn on an atomic clock?
I'll show you. Everyone is interested in time and everyone knows what a clock is, but no one can really give a satisfactory definition of time. The usual physicist definition is time is what you measure with a clock. Einstein thought about time very deeply, of course, and he gave, I think, the best description of time. He was visiting a astronomer at Harvard, and the guy, his host, had a dinner party for him, and it was a jolly evening, and guests lingered on, and slowly they left. But one couple lingered at the door and just talked on and on. They were so delighted by being in the presence of a celebrity that they stuck far too long. And when they did eventually go, Einstein said, "Those people are just like time, always going, never gone." Anyway, I'd like to take a long view of time. Just out of curiosity, what were the first observations of time in our society? These are Paleolithic carvings on stones. There were some found on stones, some on large stones. These were discovered in the 1970s by a paleontologist, Alexander Marshak. And by studying a lot of these stones, you could decipher a pattern on them. The pattern starts there and winds around. This is a calendar. These show the various phases of the moon, and it allows you to know how many weeks you are from where you started. At the time these were created, there had been no agriculture. That had not yet been discovered. It was clearly a hunting and gathering society. And when you went out to hunt, you had to know the season at times quite precisely because herds moved around and you needed to be where they were. So this is the way they kept time then. A little bit later, things got to be rather sophisticated. This is a tumulus in Ireland. It's a burial spot. This large hill over here, it was all piled up. It was man-made, and it was a burial plot for kings. Here is an entrance to the tumulus on one side. This wall on the outside has been reconstructed. It had pretty well collapsed, but there is a tunnel in here leading through to the center of the tumulus. It's about 100 meters long. It's rather low, but you can get in there. And at the center of it is a chamber where they interred, well, they didn't inter, they had the remains. They would cremate their kings and carry them into this chamber and put their ashes in a little niche in the wall. After many, many years, they would dispose of them and put the most recent kings there. So it was really a burial chamber. When you walk into the center, you have to bend over because it isn't that high. And when you get into the middle of it, it is totally dark, rather spooky. And you sort of wonder what's going on. You're a good deal below the surface. But our tour guide who showed us had a switch. There was a light bulb over this window. And when you turned on the light bulb, the chamber you were in, which is about, it's probably about 8 meters high, just lit up. It blazed. When you walk in, you're actually walking slightly up. You don't notice it, but so far up that when you're in there, you can't see this window at all. when the light comes through, it grazes off the stones on the floor, which are polished, which act like mirrors, and the whole place just lights up. Now, the ancients, of course, did not use electric lights. They used the sun, which shone through here at the winter solstice. So this was a way of measuring the beginning of the year every year, of marking that. So that gave a guideline on their compass. This let them decide how long the year was going to be. They would know when the seasons were coming. So this was both a religious structure, but a observatory. You observe the sun at its lowest point on the horizon. So what was interesting to me was that this chamber in the center had been totally untouched. Although the things had collapsed on the outside, the tunnel going in and the chamber stood this way. This is dated roughly the same time as Stonehenge, about 3,000 years BC. So this thing had stood weather and the other deprivations for 5,000 years, which is pretty good construction. We visited Ireland in 2011 and visited the Gallus oratory in Dingle. This is on the west part of Ireland. The tumulus is on the east side, but it's the same construction. It's Corbel construction. Now, the outside of this has had some reconstruction to it, but the inside hasn't been touched. This is actually a small church. It was used by priests, Catholics, with one priest and 4 laymen could sit in there, and it's oriented towards the east, as all churches are. So this is just an example of construction. It has nothing to do with time, but to be able to do such beautiful stonework. And the stones were imported, they weren't local stones. Just shows the sophisticated technology there. Well, now let's move forward a little bit. 700 years. I'd like to go to this little castle, which is on an island near, off of Denmark. This is Tycho Brahe's palace. Tycho Brahe was a nobleman and a gentleman astronomer. He had in this a device for finding the ephemeris, the paths of the planets. It consisted of this quadrant over there, which was calibrated very carefully. And there's a window over there. And you could look along the quadrant through the window and watch the stars go by, which they did fairly frequently, and you could also watch planets go by. And if you measured the time the planet went by, and here's a clock down here, it looks like a grandfather's clock, but the grandfather's clock wasn't invented for another 50 years. But anyway, it is someone who keeps time. So you know the latitude or the altitude of the trajectory from these angles here, and you take time, and that's how astronomy was done by him. And he was fabulously precise in his astronomy. He loved taking data, but he wasn't very much good at math. And so he always had someone else analyze the data for him. And who he got to analyze the data was Kepler. Brahe was actually sort of expelled from his island for being too arrogant and abusive to the natives. And he went to Prague, and Kepler went along with him. And they set off just on New Year's Day, 1600. And he set off to make new planetary tables. Kepler was a fascinating person. He had, as I put it here, 1 foot in medieval alchemy and 1 in modern science. The reason that people were astronomers in those days was so that they could be astrologers. There was a great market for astrologers. Every king had to have a good astronomer working for him. He did not believe in alchemy. Kepler knew that, that astrology was bunk. And the reason he knew it was bunk is he knew that the planetary positions were not known that well. The astronomers were using bad data, and his goal was to get really good data. So he was going to do accurate measurements on the ephemeræ of the planets in order to make honest people of astrologers. That's why he had 1 foot in the Middle Ages and the other foot in modern science. But his measurements were, his interpretations of Brahe's data were marvelously precise, and he discovered what the actual paths of the planets were. And his first discovery was that they're not circular. Well, I should say that he worked first on the planet of Mercury. And he discovered that it was an ellipse rather than a circle. And that was big news. It was very upsetting. The world at that point really had accepted the solar theory of Copernicus. Everyone knew that the planets went around the sun, except maybe the Pope. It was known really to the Greeks. So that really wasn't upsetting. But the fact that the planets did not move in perfect circles really was. And this caused tremendous friction at the time and upset. He also discovered what we call the law of equal areas. Today we'd call it conservation of angular momentum. But he did that, didn't know about angular momentum, but he did know that if you look at a line from the sun to a planet and look at the area it sweeps out in a certain time, it's the same, whether the planet is moving fast, far from the sun, or slow, far from the sun, or fast, close to the sun. So those are the first two of the planetary laws. These were exciting years because in 1609, Galileo learned about the telescope and got his hands on one. In December, started taking systematic observations. The telescope wasn't very good. This is a model of it, which is still in the Science Museum in Pisa, no, in Florence. He started looking towards the middle of March, the middle of December. And in March, just 3 months later, he published his results, much quicker than any journal can publish results like that now. He not only took a lot of data, he wrote it up and published it for good reasons. The publication, called the Starry Messenger, was dedicated to the Medici. What is the name of the Medici? Anyway, to the Medici family. They were his patrons. He wanted their patronage. And one way you earned patronage was by not making campaign contributions, but by dedicating a distinguished book. Now, from the point of view of experimental technique, Galileo was totally in a class by himself. He had only the crudest instrument. The telescope itself was very poor. Most people couldn't see anything through it. And he didn't have any sort of modern equipment for recording observations. He didn't even have the Cartesian technique of plotting points geometrically on paper. He just took notes. And fortunately, these notebooks survived. You can see on each date, he listed the date, and to show where the moons were, because, well, I didn't even mention that he discovered that that Jupiter had another star nearby, and a few days later, he noticed that the star wasn't there. So he went back and started looking, and he saw a whole bunch of stars moving around Jupiter. He immediately recognized that this was a little solar system. And he went about finding the motions of this little solar system. And he did it by making these little sketches over here. And they were remarkably accurate. Those are a plot of his data. And from that, you can find the periods of these orbits. Now, astronomy advanced very quickly in those years, and there were much better measurements about 60 years later. Here they are measured about 70 years later. They were quite well known. You notice that the Europa 84.223, from the fit to Kepler, he had 85 hours. From Ganymede, they were accurate for several of these planets, and they were used by Isaac Newton. These figures are from his Principia in the volume on gravity and well, he has his laws of motion. He's now looking at gravity. And what you do is to calculate the distance of the planets from Jupiter according to Kepler's laws, and shows that they match his calculations for the inverse square motion. What he was showing here is that these were held in place by gravity, which was assumed to vary with the inverse square of the distance, and making a connection. The force by which the moon is retained in its orbit is the same force with which we commonly call gravity. In other words, he discovered the law of universal gravitation, which is one of the intellectual milestones of modern science. So this all followed from Kepler's work. Kepler's work took him over 10 years, was terribly laborious. Precision measurements generally end up being terribly laborious. And by the standards of the time, he was making precision measurements, but they paid off. And this is one of the reasons that some physicists are obsessed with precision and making precision measurements, that you generally find out interesting new things when you measure very carefully. And time is one of the things that you can measure extremely carefully. So now I'm going to start talking about atomic clocks. So we're in early 20th century, around 1922. I'm going to take, for example, for granted, some of the facts of life that you may be, if you've studied any physics, you're familiar with it. Otherwise, you just need to take my word for it. I'm going to take for granted the Bohr model of hydrogen. This is the hydrogen atom consists of a light electron circulating around a very heavy proton. One is charged negative, the electron, the other is positive, and the force between them is an inverse square law force, just like planetary motion. With this law and some preposterous assumptions, you could describe a lot. You could describe the spectrum of hydrogen, for instance, which was a major problem then. People didn't understand the nature of atomic spectrum. They knew that if you separated light through a spectroscope, which was one of Newton's inventions, you could see lines of characteristic color, and those were characteristic of each element, but no one knew what the connection was. Well, in hydrogen, that Bohr came up with a formula which described the spectra very well. Actually, he justified an empirical formula. It had been discovered by Balmer in around 1880, and later by Rydberg kind of generalized it. But a very simple algebraic formula for the lines of hydrogen, but no one knew what it meant. If you made Bohr's assumptions, you could calculate exactly what that formula meant. So there's obviously some great truth in it, but no one really understood it because of the assumptions he had to make. The first assumption was that as the electron goes around the proton, it can't go around at any arbitrary speed and orbital size. It has just certainly allowed energy states. These are called stationary states. That was a new concept in physics, and even to Bohr, it didn't really make much sense, but that's what his theory could be interpreted as. This is at a time when our understanding of nature at the atomic level was changing very rapidly. Around 1912 to 1914, Bohr had as his first assistant a young physicist, Otto Stern. And Stern helped, acted as a listener and a discusser with Einstein on a number of important problems, mostly of a thermodynamic nature. But Einstein was very interested in this question of radiation and structure. And it's clear that his years with Einstein very much influenced Otto Stern's thinking. Because after the war, and he was tied up in the war, serving in the German Air Force. Well, of course, you didn't have much of an Air Force for the First World War. It was called their weather service. And weather forecasting was terribly important for the war because they were using poison gas. And Stern's job was to go along as an observer in the planes which were looking at the enemy and try to calculate where the poison gas might go. And on one of these journeys, when they landed, it was a crash landing, and he never went in an airplane again in his life. But after the war, things were more peaceful. He went to the University of Frankfurt and started doing remarkable experiments. He started what was called molecular beams research. Now, he didn't invent molecular beams. A molecular beam is simply an apparatus under high vacuum in which a little stream of atoms just are allowed to flow in. Since they are going into a vacuum, they don't bump into anything. They sort of travel through a straight line. And it turns out this is a very powerful technology for doing physics. And Stern was the first person to recognize the scientific possibilities with this new technology. And he started by measuring the speeds of molecules. He measured the speeds of molecules by letting the stream go through a collimating slit, and then it hit a rotating drum, a big rotating glass drum with a slit in its side. And whenever that slit went by the atomic beam, atoms would enter the chamber, fly across it, and they would make a pattern on the wall. But the fast ones would get there first, so they made the one pattern. The slow ones came later. So you had a trace which spread out in time the velocity of the atoms. And that's how we actually measured what we call the speed distribution of atoms in a beam. Now, that was well understood from theoretical grounds, particularly by Boltzmann and also by Maxwell. So the law was known, but it had never been observed. And there was some question as to its validity. The question had to do with possible 0-point energy of the atoms. And I must say, I don't understand just why they were that interested, because zero-point energy wasn't a clear concept then. Anyway, they measured it. And actually, the distribution, it's sort of a Gaussian times the square of the velocity. You know, v squared times e to the minus something times v squared. One of the discoveries right then is Stern, who's a very careful measurer, discovered that it starts out not as v squared, but v cubed. And Einstein, who visited him, they remained friends, you know, over their careers, pointed out that in a molecular beam, the faster atoms get out sooner. So you'd expect another power of v in the distribution law. Anyway, he measured the speeds of molecules, and then he conceived a totally original and spectacular demonstration of the weirdness of quantum mechanics. It was called the Stern-Gerlock experiment. Now, this takes a little explanation, and in fact, no one could explain it at first, but this is how it worked. An atom with a single valence electron is very much like an electron rotating around a positive charge. It goes around very fast. It makes a current loop. Now, a current loop has what we call a magnetic moment. It generates a little magnetic field, and its forces occur in a magnetic field. The current loop is somewhat analogous to a little bar magnet. You know, it has a plus pole and a minus pole, and if you put it in the Earth's magnetic field, it tends to rotate like a magnetized needle floating on a little cork on the water, like a compass. It twists. But if the magnetic field is not uniform, but is increasing rapidly, one end is pulled more than the other end, and it moves. Now that kind of field is it's called an inhomogeneous magnetic field. And he passed these silver atoms to an inhomogeneous magnet. Now, what you'd expect is that the atom is going to it will experience a force in this field, and it will be deflected. So here's an apparatus over here. They actually use silver atoms. So this was a little oven, and there are a couple of slits to define the atomic beam. It goes between these magnets, and the magnet poles, you can see this one is pointed and this one is concave. So it's a diverging magnetic field. It causes a gradient and it deflects the atoms. Now, what was unexpected here is that they were deflected either up or down. Come on, back. Here's the pattern. These are the ones deflected up. Here are the ones deflected down. There are none in the middle. Now, by common sense, these atoms should be able to point in any direction at all. You'd expect a smear here rather than a well-defined trace. And this was a conundrum, a deeply troubling result. The question was, how does the atom know which way to point? Why does it always point up or down, but never in between? We understand that now. Quantum mechanics explains this very easily. But at the time, this was really quite shocking. Now, a young American physicist, Robbie, came to work with Stern shortly after the experiment was done. And I knew Robbie. He told me, and he's written about it, of the shock of this experiment. They had a constant stream of visitors to the laboratory who wanted to see the apparatus and see the data for themselves and convince themselves that such a thing could be true, because it was totally counterintuitive. it was an absurd observation to go along with the Bohr's absurd model of the hydrogen. So this is very influential in the creation of quantum theory, which was created within the next decade in its modern form. Now, this young American who visited him in the sort of he was there from 1925 to 27 in that area. He went to Europe to learn about what was going on in physics. Robbie was a self-taught person in the sense that he came from a very religious Jewish Orthodox family, which was opposed to him going into science at all. There was a conflict with his parents. He discovered the library and started reading for himself and became hooked on science. He went to Columbia University and he went through and he got a PhD. And with some friends there, they started reading the European journals. There was very little communication between the US and European science at the time. We were very isolated. But he could read these journals and see the troubles which were brewing there and the complexities. He had a small group of friends and they had a little conversation group to meet and read the articles. And as soon as he got his PhD, he determined to go to Europe for himself. And he got a scholarship, a fellowship, which paid his way. He went to Europe. He went to Bohr. He just walked in to the Bohr Institute and said, Robbie, I've come to do physics. The secretary said, well, Professor Bohr isn't here right now, but if you sit down, he'll be back in some days. And he talked with Bohr, and Bohr arranged places for him to go. The first one, he went to Munich to work with Arnold Sommerfeld. Arnold Sommerfeld is a very distinguished theorist, but Robbie was impatient with him. Sommerfeld was getting on in years then, and he was very much stuck to old ways of looking at things. And Robbie had the sense to know that this isn't really where the action is going to take place. So Bohr got him a position with Wolfgang Pauli at the University of Frankfurt. Pauli was a young tiger then. He was well known as a brilliant physicist and a very abrasive person. But somehow at Frankfurt, Robbie got on very well with Pauli. Maybe that's because Robbie himself could be abrasive. But in any case, they got on well. And Pauli suggested while he was there, he might want to see what Otto Stern is doing. So Robbie just wandered into Stern's laboratory, saw what he was doing, and decided that really sounds kind of interesting. And he came up with a very useful idea for Stern. And Stern said, well, why don't you do it? Well, Robbie came to learn to be a theorist, but he became an experimenter. He did the experiment, it worked, and he was just delighted. And so his career changed from theory to experiment because of that encounter. And he started thinking carefully about how to use Stern's ideas for measuring things. And when he got back to Columbia, which gave him a position then, a very lowly position, which was in 1930, he started putting together an experimental program of his own, which was very difficult because he was given a huge teaching load and of course very little money. But he set out and started doing experiments on the deflections of atoms. Now, the question is, what can you learn about the deflections of atoms? They follow sort of classical motion. You can predict the path that they'll take, like this one over here. We're using Stern-Gerlach magnets over there. Oops. They're deflected one way by this magnet and here another way by that magnet. What you could do by looking at these magnetic deflections is you could measure not only the magnetic moment of the atom as a whole and its angular momentum, you could tell how the atom, the electron, interacted with the nucleus. It interacts electrically. The nucleus is shielded by the closed shell electrons. Nonetheless, the whole assemblage then of the nucleus and closed shell electrons carries one positive charge. The electron has a negative charge, so it behaves very much like a hydrogen atom. And you can see, and so you can calculate its trajectory. Now, what's very important over here is the angular momentum of the system, if you like, which way it points. For a single electron, it would point only in one of two directions. That's what the Stern-Gerlach experiment showed. But actually, the nucleus itself carries angular momentum, and the electron and the nucleus interact. And the result is the total angular momentum of the atom can be much more than the angular momentum of the electron by itself. And so these were methods for measuring the magnetic interactions between the electron and the nucleus. They were methods of measuring the angular momentum of the nucleus, and the nucleus has intrinsic angular momentum. It's called nuclear spin. And there was a good deal of interest in nuclear spin because nuclear spin depends on what the nuclear constituents are. So this is a powerful tool really for studying nuclear physics. And the early atomic physics in this country was all motivated by nuclear physics. So Robbie went to work measuring spins and magnetic moments of various atoms and nuclei, and it was a very productive period. He got a small group of people working with him in the molecular beams laboratory in Columbia. Then in 1936, this started in 1931, by 1936, he had measured many of these spins and moments by his deflection methods, just by seeing the trajectories of these. And then he hit upon the idea of molecular beam magnetic resonance. Here is a deflection magnet in one direction and there is in another direction. If this atom just moves through without changing its orientation, it goes back and is hit by a detector. If it's going too slowly, it goes there. If it goes rapidly, it goes down there. But for the velocities in the middle of the speed distribution, it gets into the detector. Now, what Robbie added over here was this region in the center. This is a uniform magnetic field. It doesn't deflect the atoms, but they have to go through the center over here. And what he did at the center of the field was to apply an oscillating radio frequency magnetic field. Now, if the frequency of that field corresponds to the separation of the energy levels of this system of an electron interacting with the nuclear spin, it will cause the spin to reorient, and the atom will no longer get through there. It'll be deflected in the wrong direction over here and not make it. So if you look at the flux of atoms over there and vary the frequency over here, you can measure the energy spacing of these levels in the atom. This was a revolutionary discovery, molecular beam magnetic resonance. It allowed you to make these measurements with high precision rather than just looking at crude deflection experiments. And the reason for that is what you're measuring in this experiment isn't a intensity of the beam or it's the shape of its trajectory, but a frequency. And frequency was and still is one quantity in physics that you can measure with high precision most easily. So this was the birth of molecular beam magnetic resonance. This was discovered in the January of 1937. I know the date because one of the youngest experiment in the lab was Norman Ramsey. Ramsey went there in September of 1936 and started working, wanted to work with Robbie, and Robbie discouraged him. He said he thought that all the interesting things you could do with molecular beams had been pretty well done, and he encouraged Ramsey to look elsewhere. Somehow Ramsey disregarded the advice and started working with the group in September. In January, Robbie hit upon this idea of magnetic resonance, and the fun just began. And the whole laboratory went into working at high rate, many new discoveries. You could make measurements you could make very quickly, and Norman participated in all of that. So they worked through 1937 up to November 1940. In November 1940, Robbie left and went to the MIT radiation laboratory. The United States was not at war, but it was clear that war was coming, and that it was clear that radar was going to be a crucial tool in the war, and the Rad Lab was set up to develop radar, and Robbie went there as its scientific director. His research essentially stopped at that point. Everyone's research stopped through the war, but by the end of the war, Robbie was no longer really a research scientist. He'd become a great statesman of science and had many obligations. So he didn't do further experiments himself, but he built up a fantastic physics department at Columbia. That physics department in the coming years won 8 Nobel Prizes for work which was done at Robbie, for which Robbie was successful, in starting. He mentored these experiments. So that's really quite extraordinary. And that was only one of the many things that he did. So he received the Nobel Prize for inventing molecular beam magnetic resonance rather quickly. He received the 1945 prize. The 1944 Nobel Prize had gone to Otto Stern for inventing the molecular beams method. They gave it the following year to Robbie for discovering molecular beam magnetic resonance. He received the Nobel Prize in New York. Otto Stern was in this country at that time, and they both received it at the same ceremony. It was held in the Swedish embassy because the war was still on and they couldn't go to Europe. Anyway, Stern got it in 1944. Robbie got it in 1945. He got it in December of 1945. And he gave a talk to at the American Institute of Physics, actually. It was some sort of physical society meeting. But there was a very good science reporter at the time, William L. Lawrence, and he reported on what Robbie talked about. And what Robbie talked about was the possibility of making an atomic clock. He would like to see someone build an atomic clock that would be capable of providing for the first time a terrestrial check on the Einstein postulate that the gravitational field produces a change in the frequency of radiation. That was the start of atomic clocks. Now, Robbie's idea was this, that there are some of these frequency interactions in the atoms which are strong enough so that their frequency is very high. For instance, in the cesium-133 atom, there is what we call a transition at 9 gigahertz, about 3 centimeters of radiation. Now, for an atomic clock, you want something which is ticking very fast, and 9 gigahertz is a very fast tick rate. He was suggesting that if you could lock a oscillator to the frequency of that transition, it would be stable as a frequency reference for a clock. All you need to do is count the number of cycles which come along. If you want to measure 1 second, you just count 9 billion cycles. Well, you can actually do that electronically. There are various ways to do that. Einstein, it's interesting, he said he would like to see someone build an atomic clock. He didn't want to build it himself. He was very much of a purist. He didn't like doing applied physics. He felt that he'd leave that to others. And others got interested in it very quickly. I got interested in that in 1953. I went to Cambridge University as an undergraduate. I'd graduated from Williams College. And I had a tutor, a young man who was actually working in molecular beams. He was doing molecular beam magnetic resonance on radioactive atoms, the first laboratory to do that. And he told me about his research, which was very nice because Cambridge, at least then, was a very formal place, and undergraduates were carefully insulated from graduate research or from the faculty involvement. But he told me about his research. I went there as an undergraduate, I might say. I already had a bachelor's, but now I have 2 bachelors. But he told me about it, his work with molecular beams. And he told me about Robbie's speculation that you could see the effect of gravity on the rate of a clock. Now, I learned many new things then, so this was just one of them, but I remember being really startled by that idea and intrigued by the thought that gravity affects time. Well, it intrigued others too. That was sort of the motivating force for really the development of atomic clocks. This is an example of how the atomic clock works. You have 2 deflecting magnets there and there. If the atom goes and reaches there and doesn't change its orientation, gets deflected up and out of the beam. If it does change its orientation in there, it gets deflected this way. Now, it gets deflected by interacting with the radiation, and the radiation is microwave radiation. In fact, this is the frequency of radiation with a cesium transition. It interacts only there and there. The reason that you're doing it this way with what we call separated oscillatory fields, instead of just having one field in the center, is that the phase of the radiation can't change as it goes through the field. If it does, it radiates on one part of the cycle and comes back on the other part. So here, the atom starts to make its transition there, and then the radiation is cut off and it picks up over here. And the width of the resonance, which depends on how long you spend there, depends on this total transit time. Now, the width of the resonance is a terribly important thing in making measurements of frequency or energy. They're related. The longer you can make a measurement, the more accurately you can measure the frequency and find the energy. Frequency and energy are related, by Planck's relation, that the energy of a transition is just Planck's constant times the frequency. So what you really want to do is to measure the frequency very, very accurately. To measure frequency accurately, you want to count many cycles. And to count many cycles, you want to count for a long time. And that's at the heart of the atomic clock. I've put his picture up because it was Norman who invented the separated oscillatory field method, which opened the way to atomic clocks. Also, I note that it's just the 9th anniversary of his death. We were very good friends, and I was a graduate student in his laboratory. Anyway, in early 1950s, Charlie, I know that's spelled wrong. I changed it several times, but it keeps changing back. It's Gerrold, Zacharias. Zacharias was a postdoc in Robbie's laboratory before the war. Right after the war, he came to MIT and set up a molecular beams laboratory. And he went to work building an atomic clock, which was practical, what we call he called it a portable atomic clock. The device would be in this vacuum chamber here. It was on wheels. You could take it from laboratory to laboratory. His idea was to use it as a frequency standard in making atomic beam measurements. So this is the first practical atomic clock. The first demonstration of an atomic clock was in 1954 by two English physicists, Jack Perry and blah, blah, the other name will come right up. But theirs was just a tabletop apparatus. It wasn't really a useful frequency standard. Zach, and that's him standing right there, had the idea of making this practical. In fact, they did make it a commercial device. It was engineered in the national company in Malden. It was called the Atomicron, and this was the first practical atomic clock. Well, it wasn't all that practical because this cabinet is filled up with very complicated electronics. The problem was you needed to synthesize the frequencies you wanted very accurately, and this was a big chore using the electronics at the time, which is all vacuum tube electronics. But that type of atomic clock became highly developed. It's called the cesium beam atomic clock, and it's still in use today. It became the standard atomic clock. For many purposes, it still is. Now, one of the people that Robbie brought to Columbia was Charlie Towns in 1954. And Charlie Towns conceived of another type of atomic clock called the maser. I'm showing you this picture of I'll show how it works, just the picture of the actual publication. This is in Physical Review Letters in 1954. There's a little bit on this page, there's a full page, and a little more on that page. This is 1.5 pages in Physical Review Letters. In this length, he explains the principle of the maser, what it is, how it works, and he shows data, all in less than 2 pages. It's a marvel of concision, and the maser was a marvelous device, although not the original type that he invented. He invented a device which was working with a molecular transition in the ammonia molecule. And you could use this molecular transition as a frequency reference, but it wasn't a very good one. However, it inspired Norman to think about making the hydrogen maser, using the hydrogen atom. And the idea is this: you take a stream of hydrogen atoms and you pass it through, well, we'll just say a deflecting magnet. This wasn't a kind of a Stern-Gerlach magnet. It's much more sophisticated by that point. But the beam in the upper hyperfine state of the hydrogen is brought to a focus. I should say hydrogen has 2 energy levels in its ground state. They're called the hyperfine levels. And the difference between them in frequency is about 9 gigahertz. Anyway, so they're focused into this chamber here, and the atoms go and bounce around in the chamber. It takes them up to about a second to escape. So in that chamber, they're interacting with a radiation field which causes transitions. Now, the radiation field is actually due to the energy radiated when atoms go from the upper energy state to the lower state. That's the maser principle. The radiation goes into a tuned cavity, so it builds up in intensity, and if it gets high enough, it'll self-oscillate. So it's an atomic clock, but it's an active clock. It produces radiation. It's not one in which you have to generate the radiation to make the atoms change. So it's inherently a simpler device. I went to work in his laboratory in 1956. I took his course. I went from Cambridge back to Harvard University in 1955. I took Norman's course in the fall. In the spring, I started working in his laboratory. And the following fall, he told me about this idea of a storage bulb for extending the interaction time of the atoms with the radiation. Actually, at that point, we hadn't decided on using a maser for exploiting the idea, But after some discussion, that seemed to be the way to go. So I got this choice job. I was working with Norman in building the hydrogen maser. That was the goal, really, of my PhD. And this is what it looks like. Now, as usual with pictures of scientific apparatus, you can't tell a thing about it really by looking at it. These large loops over there are magnetic coils to cancel out the Earth's magnetic field. This drum in the center that you may be able to see there. This houses the resonator, which is a large cylindrical cavity with an end you could move in, and it had a little antenna in it to bring out the radiation. So that was the device. It looks big and complicated, but it's actually big and simple. Yeah, there's a picture of me in my youth. That was my first graduate student, Stuart Crampton, and there was Norman in the laboratory playing with another hydrogen maser. At this point, we've got rid of the coils and using magnetic shields. Anyway, we went to work developing the maser, and I worked with it for a few years doing various measurements on hydrogen. The original cesium clock, which had been proposed by Robbie, became the standard atomic clock. When you go to work on a device like this, you can make lots of improvements. You make big improvements and little improvements and incremental improvements. When the hydrogen maser first worked, it was our first comparisons showed a stability at the level of about a part in 10 to the 11th. Within a few years, it had become good to a part in 10 to the 13th. We didn't do that development ourselves. I was doing other experiments with the maser, but clockmaking was turned over to a group which was working for the Varian company. They were very good and carried the development quite far. The cesium clock was developed by lots of companies, ultimately by Hewlett-Packard, and it became a terrific frequency standard. It was small and compact, and it was highly precise. And as these clocks became available, new uses for them came up. So it turned into a flourishing industry. The question is how far you could go with their precision. Well, they improved by about a factor of 10 every decade for 5 decades. They came to their limit at about a part in 10 to the 15th. There was a naturally interest in going beyond that, but to go beyond that, you really would need to go to higher frequencies. You needed a higher clock rate. Ideally, you'd like to go to optical frequencies, but there was no way to facilitate that. You can't count the ticks of oscillation of a beam of light. But actually, once the laser was invented and laser improvements went on with the same incremental rapidity, it became possible. Now, to show you the obstacle in the way, around 1980, measurements of distance came to a halt. You could measure distance with interferometers to about a part in 10 to the 9th. An interferometer, I'm talking about a Michelson interferometer. Michelson learned how to measure distance by counting wavelengths of light in it. He did that simultaneously with doing the Michelson-Morley experiment. And in fact, in 1907, he got the first Nobel Prize for Physics in the United States by measuring the standard meter in terms of the wavelength of cadmium, which is a nice sharp line. And that technology was improved, but it came to a halt because you can't compare distances to better than a part in 10 to the 10th. That means that you can't measure the speed of light to better than a part in 10 to the 10th. Measuring the speed of light basically means measuring how far light goes in a given time. Time you could measure very well, the distance you couldn't measure. So what was decided was to reverse the process. Let's measure the frequency of light. And then the meter is just the distance light travels in a certain fraction of a second. In fact, the distance L is just the speed of light divided by the frequency. So that would be the new definition. But to do that, you needed to be able to measure the frequency of light. And that required a lot of hard work. The way you would do that in those days, you'd start from an atomic clock down here. It's gotten out of the picture, at least on my machine. But you take a frequency signal from your atomic clock, which is known as well as the, as time could be measured in that type, and you multiply it. It's quite easy to multiply frequencies at that range. In a nonlinear device, you amplify it in a klystron amplifier. You're starting at 3 centimeters. So you're now down to, I don't know, 4 or 5 millimeters. Then you do that again. And you do that again, you've gotten into the very far infrared where there are lasers, which you can lock to this signal. So you have a infrared frequency over here, which is known to the same precision as your atomic clock. And then you repeat that. You go up with this is another a CO2 laser times 5. You do a color center laser, a new type of laser. You multiply that by 2. You lock a helium neon laser over there, and you take that and you double it, and you get to the frequency you want to measure. This is a standard reference line, a very narrow line in an iodine stabilized dye laser. And that can be locked to this line, to that frequency. This was actually done at NIST. It was done with great labor. 5 different groups worked on this, each one a specialist on one of these steps. Groups from the United States and also from Europe. They got together and they all worked at the same time, getting this whole thing up and running and locked. And with this, they measured the frequency of this reference line. And that allowed them to measure the speed of light. But they only could measure the speed of light not quite to a part in 10 to the 10th. So it was sort of anticlimactic, but this shows you the problem of trying to work with optical frequencies. Now, if we look at the development of clocks over that time, here are cesium beam clocks. This is the first clock, the Essen and Perry clock. The hydrogen maser started working somewhere in there. Here, by 1980, you were almost in part in 10 to the 13th. In 1990, something very important happened. The Nobel Prize was given for atom cooling. I won't describe that, but using laser techniques, it's possible to cool atoms to unbelievably low temperatures. Basically make them come to rest. To temperatures, say, of 1/1000th of a degree Kelvin. In fact, they've been cooled to nanokelvin these days. But with these very, very cold atoms, you could finally implement an idea due to Zacharias. He thought of making a cesium clock by letting the cesium atoms flow vertically in a long vacuum tube and then fall back down. They would go through the RF field up and they'd go again on the way back. It separated oscillatory fields, and they could spend a large fraction of a second doing that. And he was working on that at MIT for some years, and it turned out the idea was no good. And the reason was it relied on very slow atoms in the beam, and they just weren't there. It was discovered they were all knocked out by the faster atoms coming behind them. So that was an idea which was essentially 50 years before its time. Nonetheless, it was very fruitful. because Zach had taken an offbeat MIT student into his laboratory. The student knew electronics. He had wandered into the laboratory, got interested in the clocks, particularly the fountain clock, and fascinated by what it wanted to do, and asked for a job working in the laboratory. Now, this student was Ray Weiss. He was a dropout from MIT because he went off to pursue electronics and enjoy life rather than finish his bachelor's degree. But Zach mentored him, got better and better. This is a measurement of optical precision in measuring wavelength. And the wavelength which is being measured here is hydrogen. This H over here doesn't stand for hydrogen maser, it stands for atomic hydrogen. And this is precision spectroscopy of hydrogen, which has always been a driving force for high precision measurements. It got better and better over those years until it approached the, here, yeah, it got to about, what, 10 to the 13th or 10 to the 14th, about the limit of atomic clocks. I should say the hydrogen maser also kind of moved along this line. But at this point, there was a major change in technology, which opened the way to making optical clocks. And this projection over here, this line has continued on down. And it follows this pretty closely. At the current time, people are working in the range of 10 to the 19th. This was due to a breakthrough, the optical frequency comb, a method for measuring the frequency of light. This was independently measured, invented about the same time by Ted Hensch in Munich and John Hall in the NIST, in the National Institute for Standards and Technology. These guys are both kind of experimental magicians and have devoted their whole careers to achieving higher precision. And they were awarded with the Nobel Prize for this in 2005 because it was so important. Now, Ted has sent me a few slides over here to show how it works. What you're doing is taking an optical laser. It's called a mode-locked laser. It fundamentally works by light being reflected back and forth between two mirrors. Those form the laser cavity. And the laser light is oscillating very rapidly like that. It comes back and it gets another pulse of oscillation at essentially the same frequency, and this goes on and on. So what comes out of the laser is a stream of light, which is modulated at the frequency with which it bounces back and forth in the cavity. If you look at the spectrum of such a waveform, it has a carrier in here, which is this frequency over there, and it has sidebands in it due to being chopped going back and forth. What both of them discovered was ways to make this spectrum extend further and farther. Now, as it stands right now, when the waves come back, they're not always in the same phase as the one that left. They can jitter around a little bit. And if it does that, the sidebands over here get blurred. But in principle, if they were sharp, the frequency of some sideband over here is n times the fundamental frequency, which is going back and forth. And there's a carrier frequency just due to a phase shift at each reflection, which can change. But if you make the spectrum broad enough, a full octave, which is very broad in terms of devices such as this, if you can make it broad enough, you can synchronize the whole setup. You have a frequency coming out of here, some frequency times the basic repetition frequency plus some offset frequency. And if you double it over there, you get twice that frequency plus the offset frequency. And if you lock it to a line over here, that line is coming out with exactly twice the base frequency plus this offset frequency. And if you subtract that frequency from this frequency overhead, this carrier offset disappears. This is called the optical frequency comb. And if you have this, you can do all sorts of things with it. These are some of the things that, that Ted Hench has used with it. You can take a radio frequency and you can go to an optical frequency, which you know with the same precision as this radio frequency. So you can make your light as good as your best atomic clock. You can take an optical frequency and measure it exactly, you know, divide it by any number n up to a very huge number. So you can generate radio frequencies with it. Or you can take an optical frequency, one optical frequency, and measure another. And this has opened the way to a new world of atomic clocks. Here's one of them. The two pioneers in these type of atomic clocks, so one of them is David Wineland. Here is a single ion clock. He knows how to hold a single ion in space using a combination of radio frequency and static electric fields. And there is a mercury ion sitting right in the center. And here is light, which is coming along and exciting it. Now, a single ion isolated in space is a very nice device for running a clock. It doesn't have any perturbations from other atoms around or such, but it suffers from not much signal coming out. The narrower the resonance that you're looking at, the lower the signal rate. If you want to have a signal, a resonance 1 hertz wide, you have to wait a second to get 1 photon. That's not enough signal to control any clock with it. You've got to get a signal rate higher. And there's a very clever method that they use. This is the atom that they're using over here, which is, yeah, well, it's the mercury plus ion. There are two excited states that are important here. This one over here and that one over here. This one is a metastable state. It lives not for a second, but a good fraction of a second. This one is an allowed transition. It immediately radiates if you excite it. What you do is tune a laser to this transition over here, and you see this excitation coming out at a high rate. Now, every once in a while, you excite this transition over there, and the radiation turns off. I mean, and here is a picture of that happening. Here it's radiating rapidly. It turns off. It radiates rapidly again. It turns off. You measure the average radiation coming out over there. It's radiating like mad, but it's spending a considerable amount of time in the excited state. So that gives you a practical way to make a clock. Many other practical ways to make optical clocks were opened by these ultra-cold atoms. The mercury ion is very nice because it's isolated and you can handle it very well, but you do have this problem that the signal isn't very high. You'd like to get a lot of atoms because atoms are cheap, but you don't want them to interact. You can do that these days. You can make what's called an optical, it's like an optical egg carton in space, a lattice in space, in which it can be 2-dimensional or it can be 3-dimensional. And in each one of the little potential wells, you can have one atom. With that, you could use many atoms without having them interact, because they're in separate wells and you can control the interactions between wells. You can make it large if you want. You can also make it very small if you want. So there are these two types of atomic clocks which are now being used, ion clocks and what they call optical lattice clocks. Now, these are currently working in the range of parts in 10 to the 18th, and they're probing into parts in 10 to the 19th. So this is a huge advance in metrology. The problem that one has right now is comparing these clocks. You can't compare them using atmospheric transmission, like letting them both look at a satellite, which is used now at lower precisions because the atmospheric fluctuations are too hard. You can compare them over optical fibers connecting the laboratories, which isn't easy and needs a lot of development. But actually, they did this between Wineland's laboratory and NIST in Boulder, and NIST's own laboratory no, not NIST, Hall's laboratory in the University of Colorado at GILA. GILA is the Joint Institute for Laboratory Astrophysics. It's joint between NIST and the University of Colorado, and it is sort of the center for high precision metrology in the United States. Anyway, what they did was to use a commercial optical fiber connecting the two laboratories and go back and forth. And they learned how to control the fluctuations in this, which are introduced by the fiber, enough to make comparisons of approximately part in 10 to the 17th. Now, there is a lot of work going on in Germany now at the German laboratory at Bundeswehr, where they do atomic clocks very well. And they are making atomic links all over Europe to compare these clocks. Well, look, why don't I stop right here? Because there are very interesting things to come.